Every diagram of the solar system you have ever seen is lying to you. Not through any error in the positions of the planets, not through any flaw in the labels or the orbital distances, but through what the diagram leaves out. And what it leaves out is not a footnote. It is not a minor detail. What every standard diagram of the solar system omits is 99.9% of the Sun's actual gravitational domain. The nearest star to our Sun is approximately 4¼ light-years away. That is the closest known stellar neighbor to Earth, a red dwarf called Proxima Centauri. The distance is staggering by any human measure, but here is the fact that changes the frame entirely. Our solar system may already extend more than a third of the way there. Some estimates push it even further. The home you live in, astronomically speaking, is not a compact neighborhood of planets orbiting a star. It is a vast, dark, nearly invisible sphere of frozen matter that bleeds outward into what we casually call interstellar space, and it has been doing so for 4.5 billion years. This structure is called the Oort Cloud, and understanding its true scale requires dismantling almost everything that standard science education communicates about where the solar system ends and where the universe begins. Start at the center. The Sun is a sphere of plasma roughly 860,000 miles across. At its core, temperatures exceed 27 million degrees Fahrenheit, and every second, the Sun converts approximately 4 million tons of matter into pure energy through nuclear fusion, radiating that energy outward in every direction across the solar system. The inner planets orbit close enough to the Sun that light from the star reaches them quickly. Mercury orbits at roughly 4/10 of an astronomical unit from the Sun, where 1 astronomical unit equals the average Earth-to-Sun distance of about 93 million miles. Venus sits at 7/10, Earth at 1, Mars at about 1.5. Sunlight crosses the entire inner solar system in under 25 minutes. Beyond Mars, the solar system opens into a different scale entirely. Jupiter orbits at 5.2 astronomical units and contains more mass than all other planets in the solar system combined. Saturn follows at about 9.5 astronomical units, Uranus at 19, Neptune at 30. At Neptune's distance, sunlight is already 900 times fainter than it is on Earth. The Sun, which at Earth's distance appears as a brilliant disk large enough to warm your face, would require a telescope to resolve as anything other than a bright point of light. A single orbit of Neptune takes 165 Earth years to complete. A person born at one position of Neptune's orbit would live their entire life and die before the planet returned to the same point in the sky. This is precisely where the standard diagram ends. 8 planets, a central star, and a clean fade to black. The implicit message is clear. Solar system concluded, interstellar space begins. That mental model has been reinforced by classroom posters, documentary animations, museum exhibits, and the widely celebrated moment in 2013 when NASA confirmed that Voyager 1 had crossed into interstellar space. The story felt complete. The boundary had been found and crossed. But the solar system does not end at Neptune, and it does not end where Voyager crossed. Beyond Neptune lies the Kuiper belt, a broad disk of icy bodies extending from roughly 30 to 50 astronomical units from the Sun. It contains Pluto at 39 astronomical units, along with at least 100,000 objects larger than about 60 miles across, and likely millions of smaller ones. It was not confirmed to exist until 1992, when astronomers David Jewitt and Jane Liu discovered the first Kuiper belt object beyond Pluto. Sunlight reaches the Kuiper belt's outer edge in about 7 hours. In the context of what lies beyond, it is barely a threshold. Past the Kuiper belt lies the scattered disk, a population of icy bodies in highly elongated orbits, flung outward by Neptune's gravity over billions of years. One of the most extreme objects in this region is the dwarf planet Eris, which reaches nearly 97 astronomical units from the Sun at its most distant point. Then there is Sedna. Discovered in 2003 by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz, Sedna follows one of the most extraordinary orbits of any known solar system object. Its closest approach to the Sun sits at approximately 76 astronomical units. Its farthest point stretches to roughly 937 astronomical units. Sedna takes approximately 11,400 years to complete a single orbit. It exists in a region too distant for the outer Oort Cloud's typical population and too detached from the planets for Neptune's gravity to explain its position. It is a boundary object, a physical artifact of processes operating at scales far beyond anything astronomers had mapped before. And it points unmistakably towards something much larger. At roughly 120 astronomical units from the Sun sits the heliopause. This is the boundary where the solar wind, a continuous torrent of charged particles streaming outward from the Sun at roughly 1 million miles per hour, finally loses its contest against the pressure of interstellar particles and magnetic fields. Beyond the heliopause, the Sun's outflowing material no longer shapes the local environment. Voyager 1 crossed this boundary in August 2012 at about 122 astronomical units. Voyager 2 followed in November 2018 at approximately 119 astronomical units. Both spacecraft sent back data confirming they had entered interstellar space in the plasma sense, meaning the Sun's wind no longer held sway. And this is where the most consequential misunderstanding in modern public science communication occurred. When NASA confirmed in September 2013 that Voyager 1 had crossed the heliopause, headlines around the world declared that humanity's most distant spacecraft had left the solar system. News programs described it as the first human-made object to enter interstellar space. Technically, the phrasing was accurate in a narrow sense, but the implication absorbed by millions of people was this: the solar system ends somewhere around 120 astronomical units. Voyager crossed the line, story over. The heliopause is not a gravitational boundary. It marks where the Sun's wind stops, not where the Sun's gravity stops. The Sun's gravitational reach extends far beyond the heliopause, holding objects in orbit at distances that would take Voyager hundreds of centuries to reach. The heliopause sits at roughly 120 astronomical units. The Sun's gravitational domain extends to 100,000 astronomical units or more. That is a factor of nearly 1,000. Crossing the heliopause and declaring the solar system finished is like stepping off your front porch and announcing you have left your country. The actual boundary, to the extent that one exists at all, is incomparably farther away. Something is out there, far beyond where Voyager crossed. Something enormous, invisible, and ancient. The evidence for its existence has been arriving in our skies for as long as humans have tracked the heavens. The messengers are comets, specifically long-period comets. Short-period comets like Halley's Comet orbit the Sun in predictable cycles, returning every few decades or centuries. Their orbits are relatively compact and tilted only modestly relative to the plane of the planets. Most originate in the Kuiper belt or the scattered disk, gradually nudged inward by gravitational interactions until they settle into repeating paths. Long-period comets are fundamentally different. They arrive on orbits that take thousands, tens of thousands, sometimes hundreds of thousands of years to complete. They plunge toward the Sun from enormous distances, swing around it in a blaze of vaporizing ice and dust, then retreat back into the darkness on trajectories so elongated they will not return for millennia. Some have never visited the inner solar system before, completing their first close approach to the Sun since the planets formed 4.5 billion years ago. And here is what makes them so scientifically revealing. Long-period comets do not arrive from one direction. They come from everywhere. Their orbits are tilted at every conceivable angle. Some arrive from above the plane of the planets, some from below, some from the direction of Orion, others from the opposite side of the sky entirely. If you map the most distant points of their orbits on a three-dimensional diagram, those points would form not a flat disk like the Kuiper belt, but a sphere. A shell of origin points surrounding the Sun in every direction at distances of tens of thousands of astronomical units. This pattern is not random. It is a signature. It tells scientists that somewhere out there at distances vastly exceeding the planetary region, there exists a roughly spherical reservoir of icy objects from which these comets are being dislodged and sent falling toward the Sun. The reservoir must be enormous to produce comets arriving from all directions. It must be distant to explain their orbital periods. And it must contain a staggering number of objects, because long-period comets keep arriving century after century, and each one that plunges too close to the Sun and evaporates must be replaced by another from the reservoir to sustain the supply over billions of years. In 1950, a Dutch astronomer named Jan Hendrik Oort sat down with the orbital data of 19 long-period comets and noticed something striking. When he calculated the aphelia, the most distant points of their orbits, they clustered around a specific range of distances, roughly 20,000 to 50,000 astronomical units from the Sun. The clustering was too tight to be coincidental. It pointed toward a specific structure at a specific distance. A vast cloud of icy bodies orbiting the Sun at the outermost edge of its gravitational reach. Oort was not the first to propose such a structure. In 1932, Estonian astronomer Ernst Öpik had suggested a similar reservoir. But Oort had the orbital statistics and the insight to connect the observed trajectories with a physical mechanism that could explain how objects in stable distant orbits occasionally get knocked inward. That mechanism was stellar perturbation. Stars do not remain fixed relative to the Sun. They move through the galaxy on their own orbits, and occasionally over millions of years, a star passes relatively close to the Sun. Not close enough to disrupt the planets, but close enough to gravitationally nudge objects at the very outer edge of the Sun's influence. Those nudges can alter an icy body's orbit just enough to send it falling inward on a new trajectory, one that eventually carries it past Jupiter, past Mars, past Earth, close enough to the Sun for its ice to vaporize into a glowing tail. A comet is born, and its birth certificate reveals its home address. A region of space so far from the Sun that the boundary between the solar system and the galaxy itself begins to blur. Oort proposed that this reservoir is not a thin ring or a flat disk, but a sphere. A thick shell of icy objects surrounding the entire solar system at distances thousands of times greater than Neptune's orbit. The structure was named the Oort Cloud in his honor, and in the decades since his paper, every new line of evidence has strengthened the case for its existence. Scientists divide the Oort Cloud into two broad regions with distinct characteristics, shaped by different physical forces. The inner region is called the Hills Cloud, named after astronomer Jack Hills, who proposed its existence in 1981. The Hills Cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun and extend outward to roughly 20,000 astronomical units. Unlike the spherical outer region, the Hills Cloud is believed to be more flattened in shape, concentrated loosely around the plane of the solar system, shaped like a thick torus rather than a perfect sphere. It is thought to be far denser than the outer cloud, containing perhaps 5 to 10 times as many objects. Some models suggest tens of billions, or even hundreds of billions of icy bodies orbit within this inner zone. The outer Oort Cloud begins beyond the Hills Cloud and extends outward to somewhere between 50,000 and 100,000 astronomical units from the Sun, with some estimates placing the absolute outer boundary as far as 150,000 to 200,000 astronomical units. This outer shell is approximately spherical. Objects within it orbit the Sun at every inclination and in every direction. Some orbit in the same direction as the planets. Others orbit in the opposite direction. Some trace paths that are nearly circular at tremendous distances. Others follow highly elongated ellipses that carry them from the outer cloud deep into the inner solar system and back again over timescales measured in millions of years. The total population of the Oort Cloud remains uncertain because you cannot count objects you cannot see, but models based on the observed rate of long-period comet arrivals and the dynamics of how comets are dislodged suggest staggering numbers. Conservative estimates place the population at several hundred billion objects larger than about half a mile across. More generous models propose 1 trillion or more. The combined mass of the entire Oort Cloud, despite containing so many objects, is believed to be modest, perhaps a fraction of an Earth mass to as much as several Earth masses depending on the model. Though this may seem small, spread across a sphere potentially 1.5 light-years in radius, it means the Oort Cloud is one of the most diffuse structures in the solar system. The individual objects are believed to be icy planetesimals, primordial remnants from the formation of the solar system roughly 4.5 billion years ago. They are composed primarily of water ice along with frozen carbon dioxide, methane, ammonia, and other volatile compounds mixed with dust and rock. Most are small, probably a few miles across or less, though some could be substantially larger. They are dark, reflecting very little sunlight, which is itself vanishingly faint at their enormous distances. A typical Oort Cloud object receives so little solar energy that its surface temperature hovers just a few degrees above absolute zero, somewhere around 4 to 10 Kelvin. At these temperatures, even gases like nitrogen and carbon monoxide are frozen solid. These are the coldest, most isolated solid objects in the solar system, drifting through near-total darkness in orbits that take millions of years to complete. Consider Comet Hale-Bopp, which appeared in 1997 and became one of the most widely observed comets of the 20th century. Its orbital period was calculated at roughly 2,500 years, and its most distant point sits at approximately 370 astronomical units. Hale-Bopp spent thousands of years in the cold outer reaches before gravitational forces redirected it inward, where it briefly became a brilliant spectacle before retreating back into the darkness. Then there is Comet Hyakutake, which passed Earth in 1996. Before its encounter with the inner solar system, its orbit carried it to an aphelion somewhere in the range of 1,000 to 2,000 astronomical units, placing its most distant point near the threshold of the Hills cloud. Hyakutake arrived from a region so remote that when it last visited the inner solar system, modern humans were still hunting across Ice Age landscapes and painting animals on cave walls. More recently, Comet C 2025 R3 PANSDARS, discovered in September 2025 and confirmed by the Minor Planet Center, drew attention as another long-period visitor from the outer solar system. Astronomers classified it as a long-period comet with a steep orbital inclination far above the plane of the planets, exactly the kind of trajectory expected from an Oort Cloud origin. The comet reached its closest approach to the Sun in April 2026, at a distance of roughly 47 million miles. Comets like this arrive regularly, each one a fresh data point confirming that the distant reservoir is still active, still populated, still sending members inward on trajectories shaped by galactic tides and stellar encounters across billions of years. Understanding where all these icy bodies came from requires rewinding to the solar system's earliest history, roughly 4.5 billion years ago. At that time, the Sun was surrounded by a massive rotating disk of gas and dust called the protoplanetary disk. Within this disk, solid particles collided and stuck together, gradually building larger and larger objects. The biggest became the cause of the giant planets Jupiter, Saturn, Uranus, and Neptune. But the disk contained far more solid material than the planets could absorb. Trillions of smaller icy bodies called planetesimals remained as leftovers. As the giant planets grew and migrated through the disk, their powerful gravitational fields scattered these planetesimals in every direction. Jupiter, the most massive, was particularly effective. It flung planetesimals both inward and outward with tremendous force. Many were ejected from the solar system entirely, launched on trajectories that carried them beyond the Sun's gravitational reach and into interstellar space. But many others were scattered into highly elongated orbits that carried them to enormous distances without quite reaching escape velocity. They remained gravitationally bound to the Sun, orbiting at thousands or tens of thousands of astronomical units on paths that took millions of years to complete. Once these scattered planetesimals reached sufficiently large distances, the galactic tide and the gravitational influence of the Sun's stellar birth cluster began to modify their orbits. The galactic tide gradually raised their closest approach distances to the Sun, pulling them away from the planetary region and preventing the giant planets from scattering them again. Over hundreds of millions of years, this process decoupled the scattered objects from the planets entirely, trapping them in stable orbits at great distances. They became the Oort Cloud. This formation model, refined through decades of increasingly sophisticated computer simulations, explains several key features of the cloud's structure. It explains why the outer cloud is spherical, because the galactic tide randomizes orbital inclinations over time, spreading objects into a shell rather than a disk. It explains why the inner cloud is more flattened, because galactic tidal effects are weaker at shorter distances and have not had sufficient time to fully randomize the orbits. It explains the total mass, because most scattered planetesimals were ejected entirely, with only a fraction remaining bound. And it explains the ongoing comet supply, because the cloud contains enough objects to sustain a steady trickle of new comets over the solar system's entire lifetime. The formation model is closely tied to a broader framework called the Nice model, named after the city in southern France where it was developed. The Nice model describes a period of dramatic planetary migration that occurred in the first several hundred million years after the solar system formed. In this model, the giant planets originally occupied a more compact configuration, closer to the Sun and closer to each other. At some point, Jupiter and Saturn crossed a mutual orbital resonance that destabilized the entire outer solar system. Uranus and Neptune were scattered outward into the planetesimal disk, plowing through it with catastrophic effect. As they migrated outward, their gravitational influence scattered planetesimals in every direction, some inward to bombard the rocky planets in the episode known as the Late Heavy Bombardment, and others outward on highly elongated orbits, reaching thousands or tens of thousands of astronomical units from the Sun. Many of those outward scattered objects were ejected entirely, but a significant fraction remained bound, their orbits gradually shaped and stabilized by the galactic tide. These survivors became the Oort Cloud. The Sun did not form alone. It emerged from a molecular cloud, along with hundreds or thousands of sibling stars in a stellar nursery similar to the Orion Nebula. For the first few tens of millions of years of the solar system's existence, the Sun was embedded in this dense cluster, surrounded by neighboring stars at distances far closer than any star is to us today. The gravitational interactions within this birth cluster were intense. Planetesimals flung outward by one star's giant planets could be captured by a neighboring star. The galactic tide within the dense environment of the cluster was stronger and more complex than the tide the Sun experiences today. The effect of these cluster interactions on the forming Oort Cloud was profound. The dense stellar environment helped decouple the scattered planetesimals from the planetary region by raising their perihelion distances, trapping objects in stable but distant orbits before the giant planets could scatter them again. This is believed to be one of the primary mechanisms that populated the Hills cloud region. The detailed structure of the Oort Cloud, including the properties of objects like Sedna with its extreme detached orbit, preserves information about those early cluster conditions that cannot be recovered from any other source. A 2025 paper published in Astronomy and Astrophysics examined the relationship between the Oort Cloud's current mass and the Sun's early history. Their model suggests the cloud's mass, estimated at between roughly 2/10 and 2 Earth masses, is best explained if the Sun departed its parent star cluster within about 20 million years after the giant planets formed. This constrains the Sun's birth environment and directly links the Oort Cloud's properties to events that occurred at the very dawn of the solar system. But perhaps the most striking recent development arrived from an entirely unexpected direction. In September 2024, curators at the Hayden Planetarium in New York City were preparing a new show called Encounters in the Milky Way. The show included a detailed visualization of the solar system's outer regions built from simulation data provided by David Nesvorny, a planetary scientist at the Southwest Research Institute, who had spent years modeling the Oort Cloud's formation and dynamics. When the team projected the simulation onto the planetarium dome, astrophysicist Jackie Faherty noticed something strange in the visualization of the inner Oort Cloud: a spiral. Two distinct arms curling outward like a miniature galaxy, clearly visible in the data. At first, Nesvorny suspected an artifact, a glitch in the rendering or a distortion introduced by the visualization software. But when he went back to his raw simulation data, the spiral was there too. He had simply never looked at the data in the three-dimensional Cartesian coordinates that the planetarium projection used. In his standard analytical framework, the structure had been invisible. Viewed from the right perspective, it was unmistakable. Nesvorny used a NASA supercomputer to run additional simulations, testing whether the spiral persisted under different parameters, different stellar encounter histories, and different initial conditions. It did. Every simulation produced the same basic structure: a two-armed spiral in the inner Oort Cloud, approximately 15,000 astronomical units across, oriented roughly perpendicular to the galactic plane. The physical explanation is elegant. Objects in the inner Oort Cloud at distances between roughly 1,000 and 10,000 astronomical units exist in a region where both the Sun's gravity and the galactic tide are significant forces. The galactic tide, the gravitational influence exerted by the combined mass of all stars and dark matter in the Milky Way, acts on these distant objects by slowly rotating their orbital planes and modifying their eccentricities. This process, governed by a phenomenon known as causality of oscillations, does not act uniformly on all objects. Its effects depend on each object's specific orbital parameters. The result is that objects at different distances and inclinations evolve at different rates, creating a systematic twisting pattern over billions of years. This differential evolution produces a spiral structure in physical space, with two arms winding outward from the inner edge of the cloud. The spiral is remarkably stable. Nesvony's simulations showed that it formed early in the solar system's history, within the first few 100 million years, and has persisted to the present day. Even closed stellar passages, which can temporarily disrupt the outer Oort cloud, leave the inner spiral largely intact because the objects composing it are more tightly bound to the Sun and less susceptible to external perturbation. The discovery was published in early 2025 and is currently in press at the Astrophysical Journal. It represents a candidate finding, not yet independently confirmed through observation, but the physics supporting it is consistent with everything else known about galactic tidal dynamics. The Milky Way's gravitational field has literally sculpted the structure of the solar system's outermost region, twisting it into a pattern that echoes, on a vastly smaller scale, the spiral structure of the galaxy that created the force responsible. The inner Oort cloud carries the fingerprint of the Milky Way written into its architecture. This discovery reinforces a deeper point about the Oort cloud's nature. It is not a static, frozen relic. It is a dynamic structure continuously shaped by forces operating on timescales of millions and billions of years. The galactic tide rotates orbits. Passing stars dislodge members. The giant planets scatter material outward from the inner solar system. Material flows between the inner and outer cloud regions. Comets are sent spiraling inward toward the Sun, where they briefly blaze before being consumed. The Oort cloud responds to the galaxy around it. The mechanisms that dislodge comets from their distant orbits involve forces that originate far beyond the solar system itself. Stellar perturbation is the first mechanism. The Sun orbits the galactic center, along with hundreds of billions of other stars, and over millions of years, other stars occasionally pass through the Sun's general neighborhood. A star passing within 1 light year or two can slightly alter the orbits of outer Oort cloud objects, changing their trajectories just enough to send some of them falling inward toward the Sun on new, highly elongated paths. The second mechanism, and in many ways the more fundamental one, is the galactic tide. The Milky Way contains roughly 200 to 400 billion stars along with vast quantities of gas, dust, and dark matter, all distributed in a disk and halo structure. The combined gravitational influence of this galactic mass creates a tidal field that acts on everything within the galaxy, including the outermost objects orbiting our Sun. For the planets and for objects in the Kuiper belt, the galactic tide is negligible compared to the Sun's gravity. But as you move outward through the Oort cloud, the Sun's gravity weakens while the galactic tide remains constant. At some critical distance, the two forces become comparable. The galactic tide can rotate orbital planes, increase or decrease orbital eccentricities, and raise or lower perihelion distances. When the galactic tide lowers an Oort cloud, objects perihelion enough that it begins to interact with the giant planets, the object enters the inner solar system as a new long-period comet. Research over the past several decades has revealed that the galactic tide and stellar perturbations do not merely operate independently. They work together in a synergy that explains why the supply of long-period comets remains relatively steady over time, rather than arriving in dramatic pulses. The galactic tide systematically evolves the orbits of Oort cloud, objects over long timescales, while passing stars inject bursts of random perturbation that can accelerate the process. These two mechanisms complement each other, maintaining a continuous trickle of comets from the outer reservoir into the inner solar system. Close stellar encounters are not rare events on astronomical timescales. On average, a star passes within roughly 3 light years of the Sun every 100,000 years or so. Most passages are distant enough that their effects are minor, but occasionally a star passes much closer. The most dramatic upcoming encounter astronomers have identified involves a star called Gliese 710, a small orange dwarf currently about 64 light-years away. Based on precise measurements from the Gaia spacecraft, Gliese 710 is heading almost directly toward the Sun. In approximately 1.3 million years, it will pass deep into the inner cloud at a distance of roughly 10,000 astronomical units from the Sun, possibly closer. At that distance, well within the denser Hills cloud region, its gravitational influence will be significant enough to disrupt the orbits of millions or billions of Oort cloud objects. Some will be flung outward, lost to interstellar space forever. Others will have their orbits deflected inward, their closest approach distances lowered enough that they begin falling toward the inner solar system. Over the following few million years, the inner solar system will experience a shower of new comets, visitors dislodged from the cloud's outer reaches by the gravitational influence of a passing star. Now consider what the existence of all this implies for the concept of scale. Start with something familiar. The distance from the Earth to the Sun is 1 astronomical unit, roughly 93 million miles. Light covers this distance in about 8 minutes and 20 seconds. If you could drive at 60 miles per hour without stopping, the trip would take approximately 177 years. That is your baseline, 1 astronomical unit. Neptune, the outermost planet, orbits at 30 astronomical units. Light from the Sun reaches Neptune in about 4 hours and 10 minutes. At highway speed, driving to Neptune would take roughly 5,300 years. You would have departed before the construction of Stonehenge and still not arrived. The Kuiper belt extends to roughly 50 astronomical units. The heliopause sits at about 120. These are the last landmarks most people have ever heard of. Now step into the Oort Cloud. The inner edge of the Hills cloud is thought to begin at approximately 2,000 to 5,000 astronomical units from the Sun. Take the lower estimate of 2,000 astronomical units. That is already 67 times farther from the Sun than Neptune. In raw distance, 2,000 astronomical units equals roughly 186 billion miles. Light from the Sun takes about 11.5 days to reach this point. At highway speed, the drive would take 354,000 years. But 2,000 astronomical units is only the threshold. It is where the Oort cloud begins, not where it ends. The Hills cloud extends outward to perhaps 20,000 astronomical units. At that distance, sunlight needs about 4 months to arrive. You are now 667 times farther from the Sun than Neptune. From the outer reaches of the Hills cloud, the Sun would appear as an exceptionally bright star, visually indistinguishable from the other bright stars in the sky, except for the fact that your orbit still traces a vast, lazy ellipse around it over millions of years. The outer Oort cloud begins beyond the Hills cloud and extends to at least 50,000 astronomical units. At this distance, sunlight takes approximately 9.5 months to arrive. You are now roughly 4/5 of a light year from the Sun. The Sun still shines as the brightest star in your sky, a brilliant pinpoint roughly as luminous as Jupiter appears from Earth. But it is nothing more than a point. No visible disk, no perceptible glow on the surfaces around you. No warmth reaching across that staggering vacuum. You are still orbiting the Sun, still gravitationally bound, still technically inside the solar system, but the experience of being in the solar system would be completely unrecognizable. Now push to the estimated outer boundary, 100,000 astronomical units. This is the distance most commonly cited as the Oort cloud's outer limit, though some models suggest it could extend even farther. At 100,000 astronomical units, you are approximately 1.5 light years from the Sun. Sunlight needs 1.5 years to reach you. The Sun still shines as one of the brightest stars visible, roughly matching Sirius in apparent brilliance. But that bright point delivers no more heat or illumination to your surroundings than Sirius delivers to Earth, which is to say effectively nothing. The Sun is still bright. It is simply no longer a sun. It is a star, one brilliant point among many, offering light you can see but never feel, and you are still inside the solar system. 1.5 light years. Hold that number for a moment. Proxima Centauri, the nearest known star to the Sun, lies at approximately 4.25 light years. If the Oort cloud's outer edge sits at 1.5 light years, then the Sun's domain extends more than 1/3 of the way to the nearest neighboring star. Some estimates push the outer boundary to 2 or even 3 light years, meaning the solar system might reach halfway to Proxima Centauri, possibly even farther. The space between our Sun and its closest stellar neighbor is not empty interstellar void from edge to edge. A significant fraction of that gap may still belong to our solar system, filled with trillions of icy bodies tracing vast orbits in frozen darkness. To feel the scale through time, consider Voyager 1. As of 2026, Voyager 1 is approximately 165 astronomical units from the Sun. It has been traveling for nearly 49 years and has not yet crossed 0.2% of the distance to the Oort cloud's outer edge. At its current speed of roughly 38,000 miles per hour, Voyager 1 will reach the inner edge of the Oort Cloud in roughly 300 years. It will not exit the outer boundary for approximately 30,000 years. 30,000 years. When Voyager 1 finally leaves the Oort Cloud, the entire span of recorded human history from the earliest cave paintings to the present day will have elapsed roughly once during the crossing. The spacecraft will have been traveling continuously for over 30 millennia and will only then have passed through the Sun's outermost sphere of gravitational influence. Communication across these distances presents its own kind of vertigo. Radio signals travel at the speed of light. If humanity ever sent a probe to the outer Oort Cloud at 100,000 astronomical units, a command transmitted from Earth would take a year and a half to arrive. The probe's confirmation signal would take another year and a half to return. 3 years of silence between a question and its answer. If something went wrong, mission controllers would not learn about the failure until 18 months after it happened. Any corrective instruction they sent would not arrive for another 18 months after that. The probe would be on its own in every practical sense. A machine operating in a darkness so remote that even light, the fastest messenger the universe allows, cannot bridge the gap in less than a year. Volume scales with the cube of the radius. If the Oort Cloud's outer boundary is more than 3,000 times farther from the Sun than Neptune, then the volume of the Oort Cloud sphere is roughly 37 billion times larger than the volume of the sphere enclosing the planetary solar system. 37 billion times. The planets and moons and asteroids and Kuiper belt objects all reside within an almost inconceivably tiny fraction of the total volume claimed by the Sun's gravitational domain. Think of it this way: if the Oort Cloud were a sphere the size of Earth, the planetary solar system at its center would be a sphere roughly 4 kilometers across, a small hilltop village swallowed inside an entire world. All 8 planets, all their moons, the asteroid belt, the Kuiper belt, every spacecraft humanity has ever launched, every photograph ever taken of a solar system object, all of it fits inside a volume that, relative to the Oort Cloud, is smaller than a village compared to the entire globe. If you drew the Oort Cloud as a circle the size of a classroom wall, the planetary solar system at its center would be smaller than the period at the end of this sentence. Not a small dot, the period, the full stop. That is the entire realm of human space exploration. Every mission, every flyby, every landing, every telescope image, reduced to a punctuation mark inside a sphere that extends to the walls and far beyond. Any diagram that shows the planets large enough to see necessarily truncates the solar system at Neptune. Including the Oort Cloud at the same scale would require a sheet of paper stretching from one end of a football field to the other, with the planets clustered in an invisible speck at the 50-yard line. The familiar diagram is not a simplification. It is a radical amputation, showing you less than 1/billionth of the real structure and asking you to treat it as the whole. In a scale model where the Sun is a basketball and Neptune sits half a mile away, the inner edge of the Oort Cloud would begin roughly 33 miles from the basketball. That is already outside most towns. The outer edge at 100,000 astronomical units would sit approximately 1,600 miles away. In the United States, that is the distance from New York City to Denver. In Europe, it is the distance from London to Moscow. The basketball Sun sits on the sidewalk. Neptune is a small bead down the road, and the outer boundary of the solar system is in a different time zone, requiring a transcontinental journey to reach. Neptune orbits at 30 astronomical units. If the Oort Cloud extends to 100,000 astronomical units, then Neptune orbits at 0.03% of the solar system's total radius. 0.03%. The outermost planet sits so close to the Sun relative to the full extent of the solar system that it barely registers. The Kuiper belt, stretching to 50 astronomical units, sits within the innermost 0.05%. The heliopause, where the solar wind stops, sits at roughly 0.12%. Everything that has ever been described as the edge of the solar system is within the first fraction of 1% of its actual extent. Every mission NASA has ever flown, every planet humanity has ever photographed, every probe that has ever returned data from the outer solar system, all of it has operated within the innermost fraction of 1% of the Sun's domain. Voyager 1, humanity's most distant emissary, after nearly half a century of continuous travel at 38,000 miles per hour, has crossed less than 0.2% of the distance to the Oort Cloud's outer edge. Sunlight obeys the inverse square law, meaning its intensity decreases with the square of the distance from the Sun. At Neptune's distance, sunlight is already 900 times fainter than on Earth. At the inner edge of the Oort Cloud, it has faded to roughly 1/1,000,000th of its strength at Earth's surface. At the outer boundary of 100,000 astronomical units, the Sun's light delivers roughly 1/10,000,000,000th of the intensity it provides at Earth. An Oort Cloud object at that distance receives so little sunlight that the combined glow of distant stars scattered across the galaxy contributes a comparable amount of illumination. The Sun remains one of the brightest stars visible, but that brightness carries no warmth across that distance, stirs no weather, melts no ice, and sustains no liquid water. It is a beacon whose beam has thinned to nothing long before reaching the shores it was meant to guide. Now consider the mass. The Oort Cloud, despite containing perhaps 1 trillion or more individual objects, has a total mass that is startlingly small. Current estimates range from as little as a fraction of an Earth mass to as much as several Earth masses depending on the model and which regions of the cloud are included. For context, Jupiter alone has a mass of roughly 318 Earths. Saturn weighs about 95 Earths. Even Uranus, the least massive of the giant planets, weighs roughly 14.5 Earths. The entire Oort Cloud, stretching from thousands of astronomical units out to 100,000 or beyond, spanning light years of space and containing trillions of individual bodies, may be less massive than Uranus. It may weigh less than a single ice giant planet. The most voluminous structure in the solar system is also one of the least massive. The average density of the Oort Cloud is so low that expressing it as a meaningful number requires notation with many negative decimal places. If you traveled through the Oort Cloud in a spacecraft, you would have no sensory evidence of its existence, no thickening of surrounding material, no increased frequency of particle impacts on your hull, no change in the starfield outside your window. You could cross the entire Oort Cloud from inner edge to outer boundary and never once encounter a detectable object, never once register a gravitational anomaly, never once have any reason to believe you were inside a structure at all. The Oort Cloud is there, confirmed by every line of evidence that comet science can bring to bear, and it is simultaneously almost nothing, a ghost written in gravity and statistics rather than in matter dense enough to see or touch. If you plotted the positions of roughly 1 trillion objects spread throughout a spherical shell, between 20,000 and 100,000 astronomical units, the average distance between any two neighboring objects would be on the order of several billion miles, roughly 10 to 30 times the distance from the Earth to the Sun. That is not a crowded environment. That is a void punctuated by the occasional frozen mountain, separated from its nearest neighbor by a gulf comparable to the distance from the Sun to Saturn or beyond. An observer sitting on one Oort Cloud body and looking in every direction would see nothing. No nearby companions, no glinting surfaces catching faint sunlight, no sense of belonging to a population at all. Just stars and darkness indistinguishable from any other patch of deep space. The orbital evidence for the Oort Cloud forms one of the strongest circumstantial cases in planetary science. The orbital statistics of long-period comets demand a spherical source reservoir at great distances. The dynamics of galactic tides and stellar perturbations explain how objects are dislodged from that reservoir and sent inward. The formation models explain how the reservoir was populated in the first place through planetary scattering during the solar system's youth. The mass estimates are consistent with the known efficiency of planetary ejection processes, and now, supercomputer simulations reveal internal structure that matches theoretical predictions about how galactic tidal forces should shape distant populations of small bodies. No single piece of this evidence is definitive on its own, but together they construct a picture so consistent, so mutually reinforcing, and so resistant to alternative explanations that the scientific community treats the Oort Cloud's existence as effectively established. It is hypothetical in the technical sense that it has never been directly photographed, but it is not hypothetical in the colloquial sense of being a mere guess. It is a structure whose existence is required by the physics of the comets we observe, the dynamics of the galaxy we inhabit, and the history of the planetary system we call home. Now confront what this means for the concept of a boundary. Every map humanity has ever drawn required an edge. The coastline of a continent, the border of a nation, the property line of a yard. Maps work because they have boundaries. Clean lines separating what belongs inside from what belongs outside. The human mind organizes reality by sorting things into containers with defined limits. The solar system was supposed to have an edge. For centuries, that edge was implicit in every diagram, every model, every description of our cosmic neighborhood. The planets orbit the sun. Beyond the last planet, the solar system ends. Interstellar space begins. A clean line. Inside is home. Outside is the void. The Oort Cloud destroys this boundary. It does not blur it slightly. It does not push it outward to a new farther location where a clean line can be redrawn. It eliminates the concept of a boundary entirely. The Oort Cloud reveals that the solar system does not end, it fades. And the region across which it fades is so vast, so gradual, and so interpenetrated with the forces of the wider galaxy that no line can be drawn anywhere along its length without being arbitrary in a way that strips the line of real meaning. At the outermost Oort Cloud, the sun's gravitational pull is not zero, but it is so weak that other forces begin to compete with it on nearly equal terms. The most important of those competing forces is the galactic tide. The combined gravitational influence of all the mass in the Milky Way creates a tidal field that acts on everything within the galaxy, including the outermost objects orbiting our sun. For the planets and for objects in the Kuiper belt, the galactic tide is negligible compared to the sun's gravity. But as you move outward through the Oort Cloud, the sun's gravity weakens while the galactic tide remains constant. At some critical distance, the two forces become comparable. Beyond that distance, the galaxy's gravitational influence exceeds the sun's. Objects can no longer maintain stable orbits around the sun. They are stripped away, claimed by the Milky Way, lost to interstellar space. This transition distance is described using the concept of the Hill sphere, the region around any orbiting body within which its gravity dominates over the tidal forces of the larger body it orbits. For the sun orbiting the center of the Milky Way, the Hill sphere has a radius of roughly 1 to 2 light-years. This radius roughly corresponds to the outermost estimates of the Oort Cloud's boundary, which is not a coincidence. The Oort Cloud extends as far as the sun's gravitational authority allows, and no farther. Its outer edge is defined not by any intrinsic property of the cloud itself, but by the point at which the galaxy takes over. But this transition is not a wall, it is a gradient. There is no distance at which the sun's gravity suddenly drops to zero and the galaxy's tidal force suddenly activates. Both forces operate continuously at every distance. What changes is their ratio. Close to the sun, solar gravity overwhelms the galactic tide by factors of billions. At the outer Oort Cloud, the two forces are in rough balance, and the sun's hold on individual objects becomes tenuous, contingent, uncertain. Some objects at these distances are bound, others are not. The difference depends on the specifics of each object's orbit, its velocity, its direction, and the particular gravitational perturbations it has experienced from passing stars over the last 4.5 billion years. The outer edge of the solar system is not a boundary in any physical sense. It is a probability distribution. This boundary question is further complicated by the physical reality of matter actually crossing it. In October 2017, astronomers detected an object moving through the inner solar system on a trajectory that was unmistakably interstellar. Its orbit was hyperbolic, meaning it was not gravitationally bound to the sun. It had entered the solar system from outside, swung past the sun, and was on its way back out, never to return. The object was named ʻOumuamua, a Hawaiian word roughly meaning scout or messenger from afar. It was the first confirmed interstellar object ever detected passing through our solar system. ʻOumuamua was small, estimated at a few hundred meters across, and its exact nature remains debated. It showed no visible coma or tail, leading some researchers to classify it as an asteroid rather than a comet. Others noted a slight anomalous acceleration as it departed the inner solar system, consistent with outgassing from volatile ices hidden beneath a surface crust. Its origin star is unknown. It could have been ejected from any planetary system in the galactic neighborhood millions or billions of years ago, drifting through interstellar space until it happened to pass through our solar system's gravitational domain. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor, now known as Comet Borisov. Unlike ʻOumuamua, Borisov was unambiguously a comet. It displayed a clear coma and tail, confirming the presence of volatile ices vaporizing as it approached the Sun. Its chemical composition was broadly similar to solar system comets, suggesting that the processes of planetary formation and planetesimal scattering that built our cloud operate similarly around other stars. Borisov was a piece of another star's Oort Cloud, ejected from its home system long ago and wandering the galaxy until chance brought it through ours. Statistical models based on the detection rate of ʻOumuamua and Borisov suggest that at any given moment, there may be thousands of interstellar objects larger than 100 meters passing through the volume of space inside Neptune's orbit. The solar system is not sealed off from the galaxy. It is permeable. Objects from other stars' Oort clouds are constantly drifting through our territory, and objects ejected from our own Oort cloud are drifting through theirs. This means the boundary between our solar system and the rest of the galaxy is being physically crossed in both directions continuously by solid objects carrying material from foreign planetary systems. If the Oort cloud extends to 1.5 to 2 light-years from the Sun and Proxima Centauri sits at approximately 4.25 light-years, then the gap between the Sun's outermost gravitational territory and the nearest neighboring star is only about 2 to 3 light-years. If Proxima Centauri possesses its own cloud of distant icy debris, which is entirely plausible given that Oort cloud-like structures are predicted to be a common outcome of planetary formation, then the outer edges of the two clouds may approach each other across the intervening space. In this picture, the space between stars is not a vast empty desert, with isolated oases of planetary systems scattered through it. Instead, each star sits at the center of an enormous gravitational domain, its territory extending outward until it meets the territory of its neighbors. The interstellar medium is partitioned into overlapping, competing, fadding zones of gravitational influence with no clean gaps between them. You do not leave one solar system and then travel through empty space before arriving at another. You leave one star's fadding grip and almost immediately enter the growing influence of the next. The Oort cloud is also not the same structure it was 1 billion years ago. Its population has churned, its members have been exchanged, its boundaries have shifted in response to every stellar passage, every galactic tidal cycle, every gravitational perturbation from the wider Milky Way. The solar system is not a permanent structure. It is a process, an ongoing negotiation between the Sun's gravity and the galaxy's influence, with the Oort cloud as the contested territory where that negotiation plays out. This impermanence applies to the future as well. The Sun will continue orbiting the galactic center, passing through regions of varying stellar density, encountering molecular clouds, and experiencing tidal forces that change as its position within the galactic disk shifts over hundreds of millions of years. In dense stellar regions, close encounters will strip more objects from the outer cloud, shrinking the solar system's effective boundary. In quieter regions, the cloud will relax and spread outward. The solar system breathes, expanding and contracting over galactic timescales in rhythm with its journey around the Milky Way. Models of Oort cloud evolution suggest that the cloud may have lost a significant fraction of its original population over the solar system's lifetime. The domain our Sun claimed when the Oort cloud was young and freshly populated was larger than the domain it claims today. The erosion continues. 2 billion years from now, the Oort cloud will be thinner, sparser, and its effective outer edge will have crept closer to the Sun. The solar system is not only boundaryless in space, it is shrinking in time. The home we cannot fully map is also a home we are slowly losing. The Oort cloud is not merely a gravitational structure. It is a library, a vast, cold, dark archive of primordial material maintained at temperatures barely above absolute zero for billions of years. Every long-period comet that reaches our skis is a sample of material that spent those billions of years in frozen storage at the edge of the solar system before being dislodged and sent inward on its current journey. The comet's nucleus, a dark lump of ice and dust a few miles across, is essentially a time capsule. Its surface layers may have been processed by cosmic rays and the sparse interstellar ultraviolet radiation during billions of years of storage in the outer cloud, building up a darker radiation crust. But beneath that crust, the interior ice preserves the original chemical composition of the protoplanetary disk, essentially intact. When a long-period comet approaches the Sun for the first time in billions of years, or possibly for the first time ever, solar heating vaporizes the ice from the nuclear surface, releasing the preserved volatile compounds into space in the coma and tail. In a very real sense, a first-time long-period comet is releasing material into the solar system that was last in a chemically active environment more than 4 billion years ago. The water in comets has attracted particular attention because of its relationship to the water on Earth. Our planet's oceans contain an enormous quantity of water, far more than could have been retained from the material that originally formed Earth in the hot, inner solar system. Much of Earth's water was delivered after the planet formed by impacting bodies from the outer solar system. The isotopic composition of Earth's water, specifically the ratio of deuterium to ordinary hydrogen, provides a clue to its origin. Different populations of outer solar system objects have characteristic deuterium to hydrogen ratios that differ from each other and from Earth's value. Studies of multiple comets have shown that Kuiper belt comets tend to have deuterium to hydrogen ratios that more closely match Earth's oceans than the ratios measured in long-period comets from the Oort Cloud, suggesting that Kuiper belt objects may have been the primary source of Earth's water. But the picture is not simple. Some long-period comets show ratios closer to Earth's value, and the sample of measured comets remains relatively small. The question of where Earth's water came from remains an active area of research. Beyond water, comets from the Oort Cloud carry complex organic molecules that have been identified as precursors to the building blocks of life. The amino acid glycine has been detected in samples returned from the short-period comet Wild 2 by the Stardust mission. Larger and more complex organic molecules have been identified spectroscopically in the comae of long-period comets. The presence of these molecules in Oort Cloud material suggests that the chemical raw materials necessary for life were already present in the outer solar system before Earth formed, and that comet impacts may have contributed organic molecules to the early Earth surface chemistry. This connection between the Oort Cloud and the origin of life is speculative but not dismissible. It represents one of the more profound implications of the Oort Cloud's existence, that the vast frozen reservoir at the edge of our solar system may be chemically linked to the conditions that allowed biology to emerge on at least one planet in the system's warm inner core. Computer simulations accounting for the gravitational focusing properties of the Sun and the velocity distribution of interstellar objects suggest that the Oort Cloud may also contain a small but non-negligible fraction of objects that originated around other stars. These captured interstellar visitors would be physically indistinguishable from the rest of the cloud's population without detailed spectroscopic study of their composition, which is impossible at Oort Cloud distances with current technology. But if they are eventually dislodged and sent inward as comets, their compositions might be distinguishable from those of native solar system objects, providing another avenue for studying the chemical diversity of planetary systems across the galaxy. What humanity has achieved in space exploration is genuinely extraordinary. 6 decades of robotic spaceflight, missions to every planet, landings on moons, asteroids, and a comet, probes sent past the heliopause into interstellar space. By any historical measure, the space age has been a triumph. But everything we have done, every achievement, every discovery, every image and sample and measurement has occurred within the innermost fraction of 1% of the solar system's true extent. The Oort Cloud lies beyond our reach by a margin so enormous that no technology currently imagined could close it within human lifetimes. Even at the speed of light, reaching the outer Oort Cloud would take a year and a half. At achievable spacecraft velocities, the journey requires millennia. This means the overwhelming majority of the solar system will remain unexplored for the foreseeable future. Not for decades, not for centuries, for timescales that may exceed the duration of human civilization as it has existed so far. The Oort Cloud is ours in name only. We claim it as part of our cosmic address, but we cannot visit it, cannot photograph it, cannot study it directly. We know it exists because of the comets it sends us. Messages in frozen bottles lobbed inward from a shore we cannot see. Somewhere out there right now, a frozen body the size of a mountain is drifting in absolute darkness at a distance of 70,000 astronomical units from the Sun. It has been orbiting for 4 billion years. It has never been warmed. It has never been photographed. It has never been touched by any instrument or signal from Earth. It belongs to the solar system, held by the Sun's gravity in an orbit that takes roughly 18 million years to complete. From its surface, the Sun is still the single brightest star in the sky, outshining even Sirius. Yet it is nothing more than a sharp point of light that provides no heat, casts no shadow, and illuminates nothing. The constellations from that vantage point are almost identical to the ones seen from Earth, because the object is still too close to the Sun relative to the distance of other stars for the stellar patterns to shift appreciably. That object is inside your solar system. It is part of your cosmic home, and it orbits in a place so remote, so cold, so dark, and so silent that it already inhabits the emptiness between stars in every way that matters to human experience. The only thing connecting it to your world is an invisible thread of gravity extending across trillions of miles of vacuum, a thread so thin that the next passing star might sever it entirely, sending the object drifting into the interstellar medium to wander the galaxy alone for eternity. The journey to another solar system does not begin at the edge of the planetary region. It does not begin at the heliopause. It begins at the far side of the Oort Cloud. A boundary so distant that reaching it represents a challenge of the same order of magnitude as reaching the nearest star itself. The first great barrier to interstellar travel is not the distance between stars. It is the distance across our own backyard. The Vera C. Rubin Observatory represents the best near-term hope for direct detection of individual Oort Cloud objects or objects in the transitional Sedna-like region. Its legacy survey of space and time, expected to run for a decade, will scan the southern sky repeatedly with unprecedented depth and cadence, potentially discovering dozens of objects in the inner cloud region that are temporally close enough to reflect measurable amounts of sunlight. Future space telescopes with larger apertures and improved sensitivity to faint, slow-moving objects may extend this capability further. The Nancy Grace Roman Space Telescope may contribute to this search through its wide-field imaging capabilities. Beyond individual object detection, astronomers are also exploring whether gravitational microlensing, the temporary brightening of background stars caused by intervening massive objects, could be used to probe the Oort Cloud population statistically. While challenging, statistical analyses of microlensing events might eventually provide independent constraints on the cloud's total mass and population distribution. The Gaia mission, which has produced the most precise three-dimensional map of nearby stellar positions and motions ever assembled, is also enabling better predictions of future stellar encounters with the Sun, allowing astronomers to predict future comet showers with greater accuracy and to study how the outer Oort Cloud responds to individual stellar passages over time. What scientists still do not know about the Oort Cloud is in many respects more interesting than what they do know. The total population and mass of the cloud remain uncertain by factors of several, largely because the only direct evidence comes from the comets that reach us, which represent a tiny and potentially unrepresentative sample of the broader population. The exact outer boundary is unknown. Whether the cloud truly extends to 100,000 astronomical units, or to 200,000 or somewhere in between, depends on models and assumptions that have not yet been tested by direct observation. The question of how much of the cloud's mass consists of material that originally formed around the Sun versus material captured from other stars during the Sun's birth cluster phase remains open. If a significant fraction of Oort Cloud objects formed elsewhere, that has profound implications for understanding the chemical inventory of the cloud and the ways in which planetary systems exchange material across the galaxy. The spiral structure recently identified in simulations of the inner Oort Cloud awaits observational confirmation. If the Rubin Observatory or future surveys discover hundreds of Oort Cloud objects with measurable three-dimensional positions, testing whether those positions match the predicted spiral pattern will become one of the key observational goals in outer solar system astronomy over the next several decades. There is also the unresolved question of Planet 9, a hypothetical massive body that some astronomers have proposed to explain the unusual clustering of orbits among a subset of extreme trans-Neptunian objects, including Sedna and several others discovered more recently. If Planet 9 exists at a distance of perhaps 400 to 800 astronomical units from the Sun, its gravitational influence would significantly affect the inner Oort Cloud, altering the rates and directions from which comets are dislodged and sent inward. The existence or non-existence of Planet 9, therefore, has direct implications for Oort Cloud dynamics. Ongoing sky surveys are searching for this object, and the Rubin Observatory's deep imaging may finally resolve the question one way or the other. Each of these questions, when answered, will add a layer of detail to a picture that is already extraordinary in its broad outlines. The Oort Cloud's existence is not in serious scientific doubt. Its approximate scale is known within a factor of a few. Its formation mechanism is understood in general terms. Its connection to the galactic environment is well established. What remains is the detail. The precise population, the exact boundary, the internal structure, the compositional diversity, the degree of contamination by interstellar captures, and the specific history of stellar encounters that has shaped the current distribution of its members. These are answerable questions. Given sufficient observational capability and sufficient time, they are answerable within the next few decades if current and planned facilities perform as expected. The answers will not change the fundamental conclusion that the Oort Cloud is vast beyond easy comprehension, ancient beyond direct experience, and structurally dominant in any honest account of the solar system's true extent. But they will fill in the details of a picture that is currently painted in broad, confident strokes. Here is a structure that the scientific community considers effectively established, that planetary scientists treat as a known component of the solar system when building models and interpreting observations, that is cited in textbooks and referenced in research papers as a baseline assumption rather than a hypothesis requiring justification. And yet it has never been directly photographed. No image of an Oort Cloud object exists. No mission has ever visited the region where the Hills Cloud begins. No telescope has ever resolved the structure against the background of stars. The Oort Cloud is, in the strictest empirical sense, unseen. We know it through what it does, not through what it is. This is not an unusual situation in science. Many of the most significant structures and phenomena in the universe are known through their effects rather than through direct observation. Dark matter was established as a component of galaxies and galaxy clusters through its gravitational effects on visible matter decades before any direct detection candidate emerged. Gravitational waves were theorized from general relativity and inferred from the orbital decay of binary pulsars before the first direct detection in 2015. Black holes were mathematical solutions to Einstein's field equations for decades before observational evidence accumulated to the point where their existence was beyond reasonable scientific doubt. The universe routinely contains things that are real and consequential, but that require indirect inference rather than direct observation to establish. The Oort Cloud joins this list, and its inference is particularly elegant because it follows so directly from simple orbital mechanics and basic gravitational physics. Comets arrive from all directions. Their apelia cluster at tens of thousands of astronomical units. The galactic tide and stellar perturbations are sufficient to explain how objects at those distances are dislodged and sent inward. The formation models predict that a structure of the appropriate population and mass should exist at exactly those distances. The pieces fit together with a coherence that is itself a form of observational confirmation, even in the absence of a direct image. Science at its best is exactly this, the construction of a consistent, predictive, mutually reinforcing picture of how things are, built from whatever evidence the universe makes available. Sometimes that evidence is direct and visual. Sometimes it is inferential and statistical. The Oort Cloud is a monument to the inferential kind of science, to the willingness to follow the mathematics wherever it leads, even when it leads to structures so vast and so remote that direct confirmation may not be possible within any human lifetime. It is a demonstration that the universe is knowable even in its most extreme and inaccessible corners, provided we are willing to use every tool available and to follow the evidence with rigor and honesty wherever it points. You are not living in a compact neighborhood of planets. You are at the center of a sphere of frozen darkness extending more than a light year in every direction. That sphere is your home. Most of it you will never know directly, but knowing it exists, knowing its size and its nature and its history and its role in the solar system's story, is a different kind of knowledge from knowing the distance to Jupiter or the mass of Saturn. It is knowledge that shifts the frame. It changes the background against which every other astronomical fact takes its meaning. The solar system is not what the diagram says it is. The Oort Cloud is the proof. And the fact that the proof is written in the orbital mechanics of comets, in the simulated spiral arms of a structure no telescope has ever seen, in the gravitational records of 4.5 billion years of planetary formation and galactic sculpting, makes it no less real and no less worth understanding. It makes it more. If this journey through the true scale of your cosmic home changed the way you think about where you live, consider sharing it with someone whose mental map of the solar system could use some expanding. And if you want to keep following the science wherever it actually leads, subscribing is the simplest way to make sure you do not miss what comes next. The story of the Oort Cloud is still being written. The Rubin Observatory will scan, future telescopes will image. Gaia will continue refining the stellar neighborhood. The questions about Planet 9, the spiral structure, the cloud's exact mass and boundary and compositional diversity, these remain genuinely open. Each answer, when it comes, will add resolution to a picture that is already among the most extraordinary in all of science. A structure so large that the entire human experience of space exploration barely scratches its surface. A structure so old that it carries chemical memories of conditions that existed before the Earth was formed. A structure so dynamic that the Milky Way itself has sculpted its interior architecture over billions of years. A structure so fundamental that understanding the solar system honestly requires placing it at the center of the picture rather than leaving it off the edge of the diagram entirely. The Oort Cloud is vast, dark, ancient, inferred, and extraordinary. Every diagram that ends at Neptune has been telling you half a story. Now you know the rest. The question of whether the Oort Cloud is unique to our solar system, or whether all planetary systems possess similar structures, is one of the central open questions in planetary science. Current planet formation theory strongly suggests that Oort Cloud-like structures should be common. Any planetary system with giant planets will produce large numbers of scattered planetesimals. If the system formed in a stellar cluster, cluster interactions would help decouple those planetesimals and trap them in stable distant orbits. If the system is not in a cluster, stellar perturbations and galactic tidal forces would still gradually reshape distant orbits over billions of years, though the process would be slower and the resulting structure might differ in detail. Detecting Oort clouds around other stars is extraordinarily difficult. The individual objects are far too small and dark to resolve with any current or planned telescope at interstellar distances, but there are indirect ways to probe the outer regions of other planetary systems. Observations of cometary activity around nearby stars, including unusual infrared emission consistent with dust from cometary breakups, provides circumstantial evidence for active comet populations at great distances. Studies of the chemical composition of white dwarf stars, which often show traces of rocky and icy material accreted from their surrounding planetary systems, can reveal information about the outer cometary reservoirs that feed material toward those dying stars. Some white dwarfs show evidence of accreting water-rich material, similar in composition to outer solar system comets, suggesting that Oort cloud-like reservoirs around other stars are indeed sending material inward as their host stars evolve. The interstellar visitors ʻOumuamua and Borisov provide perhaps the most direct evidence that Oort cloud-like structures exist around other stars. These objects were ejected from their home systems, presumably through the same kind of planetary scattering processes that populated our own Oort cloud, and drifted through interstellar space until gravitational focusing by the Sun brought them close enough to detect. The rate at which such visitors are arriving implies that stellar systems in the solar neighborhood eject enormous numbers of planetesimals over their lifetimes, consistent with the expectation that Oort cloud populations are continuously leaking objects into the interstellar medium. If our own system is any guide, those objects represent the tip of a much larger population, still bound to their home stars in distant frozen reservoirs similar to our own. There is a final dimension to the Oort cloud story that rarely receives the attention it deserves, and it concerns the relationship between the cloud and time itself. The Oort cloud is ancient, populated by material that has remained essentially unchanged since the solar system's first few million years, but it is also a structure embedded in deep time in a different sense. It connects the present moment to the deep past through the comets it delivers. Every long-period comet that reaches our skies is a sample of primordial material that spent billions of years in frozen storage at the edge of the solar system before being dislodged and sent inward on its current journey. The comet's nucleus preserves the original chemical composition of the protoplanetary disk, essentially intact. When a long-period comet approaches the Sun for the first time in billions of years, solar heating releases that preserved chemistry into space. Observing that material through spectroscopy allows astronomers to read chemical information encoded in the protoplanetary disk when Earth was not yet formed. This archival quality of Oort Cloud objects extends to their role as witnesses to the solar system's birth environment. The detailed orbital properties of the most extreme detached objects, those like Sedna with perihelia, far too distant for Neptune's gravity to explain, encode information about the stellar cluster in which the Sun formed. Each successive generation of detailed orbital measurements of these objects tightens the constraints on what the birth environment must have looked like. The Oort Cloud is therefore not merely a reservoir of frozen matter. It is an archive of conditions that no longer exist anywhere else in the observable solar system, conditions that shaped the formation of the planets, the delivery of water to Earth, and possibly the chemical seeds of life itself. Consider the full chain of connections this implies. The Milky Way galaxy, through its gravitational tidal field, sculpted the inner Oort Cloud into a two-armed spiral structure that has persisted for billions of years. The galactic tide and passing stars continuously nudge objects from their stable, distant orbits, sending some of them falling inward as long-period comets. Those comets carry frozen water ice, whose deuterium to hydrogen ratio constrains where they formed in the protoplanetary disk. They carry complex organic molecules synthesized in the interstellar medium before the solar system existed. They may have contributed some fraction of Earth's oceans, and perhaps some of the organic chemistry that preceded the emergence of life. Every comet blazing through our skies is therefore a thread connecting the present moment to the earliest history of the solar system, and the earliest history of the solar system to the larger history of the galaxy in which it formed. The Oort Cloud sits at the center of all these connections. It is where the solar system's gravitational domain ends and the galaxy's domain begins. It is where the Sun's 4.5 billion-year history of scattering planetesimals is frozen in orbital form. It is where the galactic tide writes its signature in the architecture of distant icy bodies. It is where interstellar chemistry and solar system chemistry intermix. And it is where the comets that have crossed our skies, for as long as humans have looked upward, originate. The sheer antiquity of these objects is worth pausing on. The icy body drifting through the outer Oort Cloud, right now at 70,000 astronomical units from the Sun formed before the Earth existed. It has been orbiting the Sun, unchanged, through the entire history of life on Earth. It was there when the first single-celled organisms appeared in Earth's oceans. It was there when multicellular life evolved. It was there when plants colonized the land, when dinosaurs dominated the continents, when the asteroid that ended the Cretaceous struck the Yucatan, when the first Homo sapiens evolved in Africa, when the first cities were built, when the first telescopes were pointed at the sky, when the first spacecraft left Earth's gravity. Through all of that history, that frozen object continued its slow, silent orbit, tracing the same vast ellipse it has traced a fraction of a time since it was first placed there by the gravitational dynamics of the young solar system. It will still be there when the Sun begins to leave the main sequence in roughly 5 billion years. It will still be there, or most of it will, as the Sun expands into a red giant and vaporizes the inner planets. It may outlast the Sun itself, eventually drifting free as the white dwarf remnant of the Sun cools, and the Oort Cloud disperses into the galaxy over the following billions of years. The Oort Cloud is not just the largest structure in the solar system. It is likely the most persistent, the last part of the solar system to survive the Sun's death. Understanding this object, and the trillion others like it orbiting in the same frozen darkness, requires grasping something about the nature of knowledge at the outer edges of what science can currently access. The Oort Cloud is established but unseen. It is real but unreachable. It is ancient but barely studied. It is enormous but nearly massless. It is our home but completely unknown in detail. These paradoxes are not failures of science. They are the honest acknowledgement of how much remains to learn about the structure of the solar system that has surrounded Earth since before Earth existed. The next generation of observatories will begin to change this. The Vera C. Rubin Observatory has already begun operations in Chile, scanning the sky with a sensitivity and cadence unlike anything previously attempted. Over its first decade of operation, it may discover dozens of individual objects in the inner Oort Cloud region, providing the first direct positional data on cloud members that are not actively outgassing as comets. Each discovery will be a direct data point on the cloud's population, distribution, and dynamics. If enough objects are found with measurable motions, the three-dimensional structure predicted by simulations may begin to emerge from the data. Future infrared space telescopes, designed with sensitivity to cold dark objects at enormous distances, may eventually push detections further into the cloud. Gravitational microlensing surveys may provide statistical constraints on the total mass. Continued precision astrometry from missions like Gaia will refine the catalogue of nearby stellar close approaches, allowing increasingly accurate predictions of when and how the outer cloud will be perturbed over the coming millions of years. None of these observations will happen quickly. The Oort Cloud operates on timescales that are geological rather than human. Its comets take thousands to millions of years to complete a single orbit. Its spiral structure took hundreds of millions of years to develop. Its response to a passing star like Gliese 710 will unfold over millions of years after the encounter occurs. The science of the Oort Cloud is therefore science practiced on cosmic time, where the payoffs of today's observations may not be fully understood until generations of researchers have built upon them. This is not a reason for impatience. It is a reason for the kind of sustained scientific attention that the Oort Cloud has been slowly receiving since Oort's original 1950 paper. 75 years of theoretical refinement, observational constraint, and computational modeling have taken the cloud from a speculative idea supported by 19 comet orbits to a scientifically well-established structure with a known formation mechanism, a predicted internal architecture, and a direct connection to the galactic environment that surrounds us. The next 75 years will add detail and precision to this picture in ways that cannot be fully predicted, but that will almost certainly include surprises. The universe has a consistent habit of being more interesting in its specifics than its general outlines suggest. The discovery that the inner Oort Cloud contains a spiral structure was not predicted in detail before it emerged from simulation data. The detection of an interstellar object passing through the solar system was known to be possible in principle, but was not expected to occur within the first years of sky surveys sensitive enough to detect it. The discovery of Sedna with its extreme detached orbit was not anticipated before the object was found. Each of these developments added a dimension to the Oort Cloud picture that was either absent or poorly constrained before. The pattern is consistent. The Oort Cloud keeps revealing structure and connection and complexity that the simpler versions of the story do not capture. The cometary orbital statistics that Oort analyzed in 1950 pointed to a distant reservoir. The physics of galactic tides and stellar perturbations explained how that reservoir feeds comets into the inner solar system. The NICE model explained how the reservoir was populated in the first place. The birth cluster dynamics explained the extreme detached orbits of objects like Sedna. The supercomputer simulations of 2024 revealed a spiral structure in the inner cloud. The interstellar visitors showed that Oort Cloud-like structures exist elsewhere and exchange material with our own. At each step, the picture has grown richer, more connected to the broader context of planetary formation and galactic dynamics, and more scientifically compelling. The picture is not finished. It will not be finished within any human lifetime, but it is already extraordinary. A vast, dark, frozen sphere surrounding our sun in every direction, extending more than a light year into what we once thought was empty interstellar space, containing 1 trillion or more icy remnants of the solar system's formation, shaped by the galaxy into a spiral architecture, permeable to interstellar visitors, slowly shrinking as the galaxy claims its outer members, carrying the chemical record of conditions that existed before the Earth formed. And knowable only through the comets, it sends inward as ambassadors from a shore we cannot see. That is the Oort Cloud. That is the true extent of your cosmic home. And every diagram that ends at Neptune has been telling you less than 1/billionth of the story. There is one more angle worth exploring carefully, because it touches on something that is easy to overlook in the middle of all these scale comparisons and orbital mechanics. The Oort Cloud is not just scientifically significant. It is philosophically significant in the precise sense that it changes the conceptual framework within which we understand what it means to have a home in the universe. For most of human history, the solar system was conceived as a bounded, knowable place. The planets were the furniture of the cosmos. Their distances were measurable. Their motions were predictable. Their physical properties could eventually be studied. The entire solar system was, in principle, something that a sufficiently advanced civilization could map, visit, and understand. The boundary between the solar system and the rest of the universe was a definite line, a conceptual wall between home and not home. The Oort Cloud dissolves this wall. It replaces a clear conceptual boundary with an enormous region of gradually diminishing gravitational influence that extends for light years in every direction and cannot be visited, cannot be directly observed, and cannot be fully surveyed by any technology in the foreseeable future. The Oort Cloud transforms the solar system from a bounded place into an unbounded process, from a defined neighborhood into a gradually fading sphere of influence that bleeds imperceptibly into the broader galactic environment. This transformation has a specific implication that is worth stating clearly. If the solar system has no hard boundary, and if the region between our solar system and the nearest neighboring star is already populated by icy bodies from both stellar systems, and if interstellar objects regularly cross through the inner solar system, carrying material from other planetary systems, then the concept of a clear separation between our solar system and the rest of the galaxy is a conceptual convenience rather than a physical reality. The universe does not organize itself into cleanly separated boxes. It organizes itself into overlapping gradients of influence, with each structure fading into the next across zones so large and so empty that they resist easy description. This is perhaps the deepest lesson that the Oort Cloud teaches. Not just that the solar system is larger than the diagrams suggest, but that the relationship between the solar system and the broader universe is more continuous, more porous, and more dynamically active than the clean separation implied by most depictions of our cosmic address. We are not in a box, we are in a gradient. The Milky Way does not stop at the edge of the planetary system and wait for us to step outside it. It reaches inward to the very outskirts of the Oort Cloud, sculpting the cloud's architecture through its tidal forces, stripping members from its outer edges, and sending occasional visitors across the boundary in both directions. The Oort Cloud is the place where this ongoing dialogue between the solar system and the galaxy is most clearly written. It is the visible, or rather the inferred, record of 4.5 billion years of gravitational negotiation between a single star and the larger structure it orbits. Every comet that arrives from the outer cloud is a direct product of that negotiation, an icy body dislodged from its stable distant orbit by the combined action of galactic tides and passing stars, and sent tumbling inward to briefly illuminate our skies before returning to the darkness. Watching a long-period comet cross the inner solar system, if you understand where it came from and how long it has been traveling and what forces shaped its current trajectory, is a profoundly different experience from watching a spectacle in the night sky. It is reading a message from the outer solar system, written in the language of orbital mechanics, about the condition of a structure so vast and so remote that no human instrument has ever directly seen it. The comet is a visitor from a region that we know exists, whose properties we have constrained through decades of careful science, but that we cannot visit, cannot photograph, and cannot fully understand from where we stand. That tension between knowledge and accessibility is what makes the Oort Cloud one of the most intellectually interesting objects in planetary science. It is not interesting because it is spectacular in the visual sense. It is not a nebula or a galaxy collision or a supernova remnant. It is a nearly empty sphere of frozen rock and ice surrounding our sun in frozen silence. Its interest is entirely cognitive. Understanding what it is, where it came from, how it works, and what it implies requires engaging with orbital mechanics, galactic dynamics, planetary formation theory, interstellar medium physics, cometary chemistry, and the history of scientific inference. It rewards sustained attention with a picture of the solar system that is richer, more complex, and more deeply connected to the broader universe than any simpler account could provide. And that is precisely the kind of scientific object worth understanding as completely as current knowledge allows, not because it is dramatic, not because it changes our daily lives, but because getting the picture of where we live right as current knowledge allows, is intrinsically valuable. It is one of the most distinctively human things we do, to look outward from a small rock orbiting a modest star in the outer spiral arm of a barred galaxy, and to use the patterns in the motions of distant frozen objects to reconstruct the full shape of our cosmic address, to realize that the address is far larger and stranger than any diagram has ever shown, and to update the picture accordingly, as honestly and precisely as the evidence allows. The Oort Cloud demands that update. It has demanded it since 1950, when Jan Hendrik Oort looked at the orbital statistics of 19 comets and recognized that they were pointing toward something vast and distant and real. In the 75 years since, every new line of evidence has confirmed and deepened his insight. The cloud is there. It is enormous. It is ancient. It is scientifically established. And it remains, in almost every detail that matters to direct experience, completely beyond our reach. That combination, established but inaccessible, known but unseen, ours but unvisitable, may be the defining characteristic of the Oort Cloud as a scientific object. It sits at the precise boundary between what we can know and what we can directly observe, demonstrating through its very existence that those two categories are not always the same. And in doing so, it represents one of the clearest illustrations in all of planetary science of what scientific knowledge actually is. Not a collection of things we can see and touch, but a self-consistent, evidence-constrained, predictively powerful model of how things actually are, built from whatever signals the universe chooses to make available. The Oort Cloud sends its signals in the form of comets. We have been receiving them for all of recorded history without knowing what they were saying. Now, to the extent that current science allows, we know. And knowing changes something fundamental about how this solar system, our solar system, appears against the larger backdrop of the galaxy that contains it. To make the Oort Cloud feel real rather than merely theoretical, it helps to inhabit it imaginatively, even if not physically. Imagine standing on the surface of one of the larger objects in the outer Oort Cloud, perhaps a body 20 or 30 miles across, orbiting at 60,000 astronomical units from the Sun. The surface is dark, covered in a reddish crust built up over billions of years of exposure to cosmic rays and the sparse ultraviolet radiation that reaches this far from any star. The temperature of the rock and ice beneath your feet is roughly 10 Kelvin, roughly 10 degrees above absolute zero. In every direction, the surface stretches away in irregular frozen hills before dropping off into the darkness of space. Above you, the sky is filled with stars. More stars than you would see from Earth, because there is no atmosphere to scatter light, no cities to create a glow, and this body is tiny enough that even standing on its surface, you are effectively in open space. The Milky Way blazes as a thick luminous band across the entire sky, brighter and more detailed than any view from Earth. Among those stars, one is noticeably brighter than the rest. It outshines Sirius, the brightest star in Earth's sky, by a modest margin, but it is still a point. A brilliant, steady, cold point, that is the Sun. The Sun is roughly 60,000 astronomical units away. The light reaching you from it is not warm. It delivers less energy per square meter than a candle burning a mile away. Your orbit around that distant point of light takes approximately 15 million years to complete. The last time you were at this position in your orbit, complex life was just beginning to appear in Earth's oceans. By the time you return to this spot, the details of what currently exists on Earth's surface will be entirely unrecognizable, if Earth's surface still exists in recognizable form at all. You are still, by every gravitational measure, inside the solar system. The Sun still holds you in its orbit, but the solar system from here is not a neighborhood of planets. It is not a place of activity and light and warmth. It is a single bright star in a sky full of stars, holding you in an orbit so vast and so slow that the entire recorded history of human civilization amounts to a tiny fraction of a single orbital period. The solar system extends to where you are standing. And it barely feels like home. This is the true scale of the structure we live in, not the 8 planets and their moons that fit inside the first 0.03% of the Sun's domain, not the Kuiper belt or the heliopause, or any of the other boundaries that have been described as the edge of the solar system. The solar system extends to a sphere of trillions of frozen objects, drifting through near-total darkness at distances where the Sun is nothing more than the brightest star in the sky. That is where it ends, and even that ending is gradual, probabilistic, and defined not by any hard physical boundary, but by the slowly increasing competition between the sun's gravity and the galaxy's tidal forces. Every diagram that ends at Neptune has been telling you that the familiar core is the whole story. Now you know that the core is only the beginning. The real solar system is vast, dark, cold, ancient, and almost entirely beyond our ability to observe or visit. It extends into the interstellar space it supposedly ends at. It exchanges members with neighboring stellar systems through a continuous flow of interstellar objects. It carries the chemical record of the solar system's birth, frozen in trillions of primitive icy bodies that have barely changed in 4.5 billion years. And it is slowly being eroded by the galaxy, losing members at its outer edge over timescales that dwarf the entire history of multicellular life on Earth. That is the Oort Cloud. That is the solar system's true extent. That is the full picture that the diagrams have always left out. And now that you have it, the familiar 8-planet image that opened your understanding of the solar system can be seen for what it is. Not wrong, but profoundly incomplete. A bright, warm, active core at the center of something incomprehensibly larger and incomparably more silent. The science of the Oort Cloud is ongoing. Surveys are running. Simulations are growing more sophisticated. Individual objects in the transitional zone between the scattered disk and the inner cloud are being discovered with increasing frequency. Each discovery adds a data point to a census that has been constrained almost entirely by indirect evidence for 7 decades. The Vera C. Rubin Observatory's first years of operation represent the beginning of a period in which the indirect evidence will slowly be supplemented by direct detection, not of the Oort Cloud itself, which remains far beyond any instrument's reach, but of objects in the innermost edge of the cloud's transitional zone, where distances are still enormous by human standards, but small enough that reflected sunlight remains detectable. The questions that will define the next generation of Oort Cloud science are clear. Does the spiral structure predicted by simulations actually exist in the 3-dimensional distribution of real objects? What is the true outer boundary of the cloud? And does it match the theoretical predictions based on the Sun's Hill sphere? What fraction of the cloud's mass consists of captured interstellar material? Does Planet 9 exist? And if so, how does it shape the dynamics of the inner cloud? How much water from long-period Oort Cloud comets contributed to Earth's oceans compared to short-period Kuiper Belt comets? Each of these questions is answerable in principle, given sufficient observational capability and time. Each answer will add precision and detail to a picture that is already, in its broad outlines, one of the most remarkable in planetary science. A structure so large that light takes 1.5 years to cross it. A structure so old that it predates the Earth. A structure so dynamic that the Milky Way has sculpted it into a spiral pattern over billions of years. A structure so diffuse that crossing it in a spacecraft would provide no sensory evidence of its existence. A structure so fundamental that honest accounts of the solar system cannot exclude it. The Oort Cloud is your outermost backyard. Now you know it is there. The comets will keep arriving. The galaxy will keep sculpting. The frozen trillions will keep orbiting in silence. And the science of the Oort Cloud will keep advancing, one discovery at a time, toward a complete picture of the largest and least known structure in the solar system we call home. Every new comet in our sky is a message F.